In this video, we're going to take a look at curve sketching with fractional exponents with an even denominator. You want to reference the odd denominator before you watch the even denominator video. So to look at these, we're going to use our grapher to observe what's going on. So let's go ahead and type in x to the 1/6 power, and let's take a look at our graph to see what's going on. Now, it's kind of hard to see there. I might want to zoom in to take a better look at that. So if I zoom to just to see what that looks like, we notice that it's curving. And so what it kind of sort of looks like is the top half of a parabola opening to the right. And we know that if we have an x is y squared sort of situation, we get a parabola opening to the right. Well, that's the same sort of idea here. So that's what we have when we have an odd numerator and an even denominator in this case. Now let's look at what happens in example 2 when they're both even. Now obviously when they're both even, you could reduce, and this is going to behave like x to the 1/3, which is why I want you to reference the odd video. So if we change this, and we change the 1/6 into a 2/6, it's going to behave like 1/3. So when we press the graph on this one, and we're zoomed in a little bit, but you notice that it is the S shape that we talked about in the odd video. So now we've got this S happening here. Now, we have a point of non-differentiability there in the middle where we have a vertical slope. Well, let's see if things continue to hold. So if I'm doing f of x is x to the 3/6, well, again, this one could be reduced to x to the 1/2 power. But again, we still have the odd numerator and the even denominator. So if I go back to my y equals, and now instead of 2/6, I have 3/6, and I go ahead and graph that. Well, notice it's the same shape as we got in example 1, only it's not as steep. So now we're looking at a graph that's a little bit narrower. Well, so let's continue and look and see what's going on. In example 4, now we've got f of x can be reduced, 4/6 becomes 2/3, x to the 2/3 power. Well, now notice we have an odd denominator and an even numerator. So again, it's important to have accessed the odd video first. So if we go into y equals and we check that to 4/6 and we hit graph, well, now because it reduces to 2/3, that creates our birdie situation that we talked about in the odd video. So that's going to give us a birdie. Now notice again, we have a point of non-differentiability here. Now, important to notice that in example 1 and 3, since this is part of a sideways parabola, if you think about the bottom half, which does not exist in this graph, that's why I changed colors, we do have a vertical slope there, so we have a point of non-differentiability at 0. Same thing over here. It's like a sideways parabola, so the tangent line is vertical, and we have a point of non-differentiability. So when we're actually doing the calculus for these problems, it's the same process as any other calculus problem. We need to find increasing, decreasing, changing concavity. We'll go ahead and do one of these, so let's just do example 1. So if I'm doing example 1, my first derivative would be 1/6 x to the negative 5/6, which can be rewritten as 1/6x to the positive 5/6. Clearly, when we set that equal to 0, we have a problem at 0. If we check a number to the left, if I plug in a -1 for x, since I have an odd, but an even on the bottom, I actually get an imaginary number because I have a 6th root of a negative number, so that's imaginary, which means the graph doesn't exist to the left of 0, which is consistent with what we know the picture to be because there's nothing to the left. If we pick something to the right, like positive 1, and we plug in, we get a positive 1 underneath. So we get a positive, and the graph is going to be increasing. Well, we no longer have to worry about the left of 0 because those are imaginary. So let's go ahead and do concavity to the right, and let's verify that that's going to be concave down. So our second derivative, and we're going to come back up to our first derivative and look at that, would be negative 5 over 36 x to the negative 11/6, which can be rewritten as negative 5 over 36 x to the positive 11/6. Well, again, we still have a problem at 0. I don't have to worry about things to the left because we already had imaginary numbers. So I'm only testing positive 1. When I plug in a positive 1, the top is negative, the bottom is positive, gives us a negative number. We now know this thing is concave down. So what does increasing concave down look like? Well, increasing concave down looks like that.